everybody, and welcome to today's XP Live webinar. My name is Nicole Highhouse, and I'm the Marketing Manager here in the XP Solutions Portland office. Today's webinar is a rather special event. We have speakers from HR Green joining us today who will share 2 recent flood modeling case studies with us. For those of you who are joining us for the first time, I'd like to take a moment to introduce XP Solutions to you. We are world-leading providers of industry-standard software solutions for sustainable drainage and water collection system modeling. We've been developing high-performing software solutions for over 30 years, but more importantly, we have a high focus on customer service and support. We want to make sure that our customers not only have good software tools, but that they have the support and resources they need to be successful in their work. As I mentioned, we are fortunate to have engineers from HR Green, one of the nation's longest operating engineering firms, with us today. HR Green provide civil engineering services, innovative management solutions to timely challenges, and they oversee the construction of high-profile improvement projects. Two of their engineers are with us today to do the presentation. Teresa Stadelman, on the left, you'll see, has 15 years of experience and specializes in water resources engineering, including watershed studies, flood control planning, floodplain modeling, and stormwater modeling, analysis, and design for municipal and private clients. Her specific strengths are in the areas of modeling analysis of stormwater systems, GIS analysis, urban water resources design engineering, floodplain modeling, and leading multiple discipline design teams. She has extensive knowledge of hydrologic and hydraulic modeling software applications, including XP-SWIM by XP Solutions, HEC-RAS, HEC-HMS, and HydroCAD, as well as ArcGIS, Spatial Analyst, 3D Analyst, HEC-GeoRAS, and HEC-GeoHMS. Ralph Stark has 27 years of experience and specializes in water resources engineering and has completed numerous projects involving simple to complex hydrologic and hydraulic analysis using 1D, 2D modeling systems, floodplain analysis and delineation, dam break analysis, letter of map amendment revision, detention, retention system designs, watershed studies, and master plans, and stormwater pollution prevention plan preparation, which is the SWPPP. He's very well versed in all local, state, and federal regulatory programs and has served on countywide technical advisory committees. Ralph is adept in the use of the following software applications that include HEC1, 2, TR20, TR55, Hi8, HEC-RAS, HEC-HMS, FEQ, EPA-SWIM, and of course, XP-SWIM. We also have Mike Ryan in the background. He's with HR Green. And we have John Howell, our Storm and Flood Products Manager, and they'll be answering questions as we go along. But now that I've told you a little bit about us, I'd love to know a little bit more about you. We have a poll that I'm going to launch here. And we'd like to know what best describes your position. Clearly, with 5 options available, we're not going to catch everybody's, but if you just give us a general idea, if you're a municipal storm and flood manager, maybe a utility engineer, or on the private side, are you a program or flood manager, or are you more in the down and dirty flood modeling and designing, or are we completely way off base with those options? Looks like we have quite a few folks on the private side who do the modeling and the designing. We have a handful of folks who are also more on the program management side. And we have quite a few people who are on the municipal storm and flood side. So welcome everybody. We really appreciate you joining us today. And it's my pleasure to introduce Teresa to begin her portion of the presentation.
Okay, thanks, Nicole. At this point, I will start with our first case study. The first case study that we'll be discussing today is an interior drainage analysis project for the city of Cedar Rapids, Iowa. This case study really starts about 8 years ago. 8 years ago, the city experienced a devastating flood in June 2008. Events leading up to this flood were numerous. The preceding winter was the 8th wettest on record. April of that year was the second wettest on record, and the actual 15 days at the beginning of June 2008 were record-setting as well. And throughout the watershed of both the Cedar River and the Iowa River, which start in southern Minnesota and continue southeast through Iowa, there was these record-setting rainfall events that continued to fall upon the peak as it moved down through the watersheds that June. The result of this is what you see in this photo here, and it produced the flood of record in Cedar Rapids. The river crested at just above 31 feet, and for some context, flood stage is at 12 feet. So it was a devastating flood. It produced 7 to 8 feet deep water through the downtown area. There was over $5.4 billion of damage to the community, including industry, the downtown commercial district, and large areas of residential land. Following that flood, the city began public engagement, coordination with the Corps of Engineers, started commencing with some buyouts, and really worked on the planning piece of how would they become more resilient and what could they do coming out of this disaster to be stronger in the future. The culmination of that planning work is the Flood Control System Master Plan, which was adopted in June of 2015. What that does is it provides direction for the implementation and construction of the eventual flood control system. That system includes a series of levees, flood walls, removable walls, and gates, and the system is designed to convey the same water volume as was experienced in the 2008 flood, but to do so in a safe manner, reducing the flood risk throughout the heart of Cedar Rapids. In addition, this plan creates 220 acres of new greenway within the floodplain, and in addition to the levees and flood walls, calls for a number of pump stations on each side of the river to deal with interior drainage. When we look at the area here through Cedar Rapids, you can see the river going the middle right there, but and that's where the flood control system will be built, is close to the river. But as you can see, that there's quite a large contributing drainage area behind that flood control system that needs to be addressed. Interior drainage, if you think about it, once you put all these barriers in place, you don't want to create a large bathtub effect where when it rains, where is that water going to go and how is it going to be discharged to the river? On the west side of the river, which is the area in particular that we have worked on, there's a 9.2 square mile watershed that drains up to where this line of protection is going to be in place. You can see that that's a much larger area when compared to the actual floodplain of the river. And looking at the aerial here, you can see that that watershed is largely developed. And in doing the planning for the flood control system, we also need to account for this interior drainage aspect. When we started the project in 2014, there was already quite a bit of background work that had been started. The Corps of Engineers had completed a feasibility study, and part of that looked at interior drainage. Specifically on the west side, they looked at this 9.2 square mile watershed and put together a HEC HMS model of that interior drainage watershed that was essentially a surface runoff model, accounted for some detention storage at the levee and for a series of 6 recommended pump stations to pump that water out over the levee into the river. Some of the items that we considered when beginning our work on the project to further this design was the existing watershed conditions. If you look at the map here, you can see just some of the topography that the watershed is quite hilly to the west and has a number of major drainage channels. Once you get closer to the river, you can see that there's a wide and relatively flat floodplain next to the river. You can also see that the watershed itself is heavily storm sewered, and so there's a lot of underground conveyance throughout the watershed. But in addition, there's also several large open channels. And so, a few things that we see here is that the situation is more complicated than an overland runoff model, and because of the heavily urban nature of the area, we need to really consider both the overland flow and the underground conveyance as well. A few other things that went into sort of the modeling updates and how we were going to set up the model to review the interior drainage. One, we needed to update the rainfall data for the new NOAA Atlas 14 precipitation values. Again, we thought it was important to create an urban drainage model where we could model the major pipes, channels, and detention areas that were present in the watershed. And knowing where water, once it surcharged to the surface, where that water went on the surface and where it collected and ponded was going to be very important to the analysis. So having that 2D gridded element as part of the model was an important consideration. Some things that we had to consider, though, when setting up this model is, it's a very large watershed at 9.2 square miles, and we're not going to model every single pipe and every single intake and we had to make some decisions about what was important to model. What would be the extent of the 1D modeling, so which storm sewer systems would be included, which channel systems would be included in the model. What would be the extent of the 2D modeling, how large should the grid extend, where we'd be concerned about surface flows and surface ponding. The grid size comes into play there when you're thinking about stability of running the model and the size of the modeling files. The interface between the 1D and 2D is important, and we'll touch on that a little bit later here. And finally, with a model, how long is it going to take to run? How much time are you going to spend running each of the different scenarios that you're going to look at? So those are all questions that we had to talk about and think about as we were setting up the model. We wanted to be able to evaluate alternative pump capacities at the various pump station locations. And finally, all this work needed to be in compliance with the city's desire eventually to have this entire system certified with FEMA. So we had to keep in mind what we need to do to meet the interior drainage requirements there. Just kind of touching on those model setup pieces here. Here's a figure again of the watershed, and the 1D portions that were included in the model are shown in magenta here. You can see we didn't model all the different pipes, especially when you look at the very upstream reaches of the watershed. We only modeled really the trunk lines, the major collectors within the storm sewer system. Additionally, we didn't model in a 2D grid the entire watershed. We limited that area to where we were most interested about surface flow and ponding to what's shown in the shaded blue here. And that's essentially the same area that had been flooded in 2008, and again is in that really flatter floodplain area along the river. At this point, I'm going to turn things over to Ralph Stark, who's going to discuss more of the model particulars going forward.
Okay, thank you, Teresa. So again, the area shown in gray there is the area we did in 2D grid, and we had to try a couple different grid spacings. We were trying to get a good definition of flow down roads, so we were aiming for a 12-foot grid size that would be comparable to a lane of road. However, that turned out to be unstable. It turns out for this project, our sweet spot was at a 15-foot grid, which then became stable, and in this case was about 26,000 grid cells. This is a picture of, we use a color ramp on the digital terrain surface, so you can see the blues along the river, ranging to the reds, which were kind of the limit of the floodplain or the flooding area. What we even found is that there were some places where water was getting trapped in here, and that we had to add in some additional pseudo drainage features to make sure the water was getting to the river. It turns out the issue was that there was an existing levee in the topography, so we actually had to punch holes through that because that's going to be replaced with the future improvement. And also on the internal side, there was also places where water was ponding. And we needed to determine whether that was real flooding areas or whether that was something with the model. So we listed off all the areas. We discussed it with the city. Some places were valid. In other places, they said, no, it really doesn't pond there that much. And we found out that we needed to add some additional interfaces, which is a way to get water back from the 2D grid into the 1D system underneath. So the little orange dots here show where we added interfaces. And those interfaces both account for not only the inlets on the main line, but they're actually, if you remember, there's a myriad of smaller branch systems and clusters of inlets that are not explicitly modeled. So that allows all of those things that would be captured by all those other inlets that aren't in the model to be brought back to the main line. Another issue that we were dealing with was the amount of runtime. This is a very large model, and initially we were actually even running it in a virtual machine that we used to share data across widely dispersed offices. However, for this size of model, we found it was definitely much better to run it on a local machine. Even running on our desktop machines, the original run was taking about 7 hours for a single storm, and the 2D grid was generating 20 gigabytes of output. But we noticed that, because this is a nested storm, where short duration storms are placed inside the middle of a longer duration storm, all the way up to the 24-hour storm. That really, most of the interesting stuff was happening towards the middle of the day where the shorter duration storms were living. And so we decided we could actually scale back the hydraulic window and only run the middle 9 hours of the storm. And that reduced our runtime to 2 hours for a single storm and to 5 gigabyte for the 2D output, which was very much needed because in running all the different scenarios that were needed for the flood for the levee certification, we actually had to run 6 different storms under 6 different tailwater conditions. So that's 36 times the 2 hour and the 5 gigabyte limits. And in fact, even by reducing this, before we had reduced this, we could only run 1 or 2 storms at a time, and then would have to come back sometimes in the middle of the night to kick off a new run, so that we could get done in a matter of a couple days. Whereas once we reduced it to the 2 hour run, there was enough memory space in the system that we could run all 6 recurrence intervals all in one run. Okay, I think Teresa was going to talk about the ponding.
Yep, I'm going to step in now and give a few examples of ways that the modeling is being used and how we're able to especially leverage the 2D results to explain and look at different scenarios of the modeling. So the first of that is when we look at the system capacity of the storm sewer system itself. We had heard and from experience know that there are locations within the existing storm sewer system where there are some capacity concerns, and where just in a rainfall event, nothing to do with river flooding or with a blocked gravity condition because of the flood control system or anything like that, but just due to capacity issues in the storm sewer system, where water surcharges to the surface and is running over land and ponding at local low points. And we are able to demonstrate that very clearly with the modeling and show where locations were that the runoff was exceeding that storm sewer system capacity and where these ponding areas were occurring that's independent of anything that we're really doing with the flood control system planning. And in doing so and identifying those, we're able to recommend a number of locations where it would behoove the city to reduce the amount of runoff and peak flow rates. Some ideas, upland detention, infiltration, green infrastructure, but ways to reduce the amount of flow that is really taxing the existing storm sewer system. Another way then that the results are being used is to show the impact of proposed storm sewer improvements. As you can see on the left here in the existing condition that there's quite a bit of ponding within the roadway. And we were able to show that, if we replace one of those overtaxed storm sewers with a new storm sewer, what the impact in terms of how much roadway ponding there would be in the proposed condition. And so that's a very nice visual to be able to share with people and explain why this improvement is important and what the impact of the improvement will be. Another thing that, in terms of planning for the future levee construction is looking at the impacts of the blocked overland flow routes. Once you put a levee in place, water can't flow down the road anymore. And what's going to be the impact? Is there going to be a ponding concern? Is ponding going to get too deep? Do we need to plan for that? So again, on the left, you see the existing condition. Once we put that levee in place, that black line on the right, you can see that water kind of stacks up behind that levee. And this, allows us to identify those locations and to plan for either increased pipe capacity from the dry side of the levee out to the river, also to look for detention opportunities where that water could be collected safely until it can be discharged. I'm going to run a short video here that will help demonstrate this. And it just shows a nice visual of how we get, ponding in the street, and it's running down the street, and then eventually that can drain out through the storm sewer system. And so it's not just the static maps that we can produce, but also the dynamic maps that really show what happens over the course of the model runs through a storm that we are modeling. So that ends really this first case study on the Cedar Rapids system. And at this point, I'm going to turn things back over to Ralph to talk about our second case study.
Okay, thank you again. So this is a project. Actually, we're going to kind of move from, we saw the last project was one that we used a unlimited license and used the full capacity of our computer processing ability. We're now looking at the next project is in northeastern Illinois, and it's also a combination of 1D, 2D modeling. In an inner south suburb of Chicago. And depending on how much you know about Chicago, there's a place where they've connected the Lake Michigan to the Illinois River to allow shipping long ago. And there's actually a second channel called the Cal-Sag. It's a separate branch that connects the Calumet River to the same system. Our area is south of that. That's the ultimate drainage point to it. We're experiencing, it's an area that's experiencing neighborhood flooding, and also due to, and actually if I can point to that, so there's a residential area in the middle here with the green lines on the north and western sides, and that has a significant 180 acres of watershed area flowing through it on its way out to a man-made channel that runs out to the Cal-Sag. And there's also storage that occurs on the undeveloped area to the west that we had to account for in our modeling. So this shows the, it's kind of a superimposition of a couple different things. Again, at the upstream, or at the top right, is the channel that we are discharging to. The middle of the screen is the neighborhood that's experienced the flooding. In red, we've colored the properties that have indicated flooding. Also superimposed with that is the depth grid from XP Swim, so we could kind of try and correlate the flooding with the houses. and to the right is to the left is the upstream storage area. So the first step was to choose which tool to analyze this in, and similar to the Cedar Rapids project, we had a combination of surface flooding with a urbanized storm sewer system underneath it. We had a downstream channel that we had data from HEC-RAS to tie into, and that we could actually pick cross-section data and flow data out of that, or actually mostly cross-section data, and be able to implement that also in the XP-SWIM software. There was an existing 24-inch sewer down the road, which the plan was to build a parallel system to that, so we needed something that could analyze the split flow and balance the flow between the two systems. Again, we had surface flow storages, we have storage areas, and we also were interested in knowing inundation depths. So all of those things put together led us to using an XP-SWIM model, because it was able to do all of those things that we were looking for. Our project, again, like I said, this was on the smaller side, so we were able to take our area of concern and trim it down to an area that we could make fit within the 10,000 cell limit that's available in all the different XP-SWIM, even the lowest level XP-SWIM licenses. In order to do that, there are certain storage areas we accounted for directly in storage nodes, particularly the larger one over to the left. And then we were also able to incorporate the HEC-RAS model data on the downhill end, so that we could not only have a static steady state water level, but that we could actually have the water level, tail water level that rose and fell with the water to the discharge into it, and we could test it out on various different types of storms. Here in northeastern Illinois, as opposed to using the nested, where we put all the different storm durations into one storm, we actually run the storm durations in separate tough duration rainfalls. As part of that, we were able to see that the downstream channel was peaking in a 2-hour storm. It was very much influenced by short, intense rainfalls, whereas with all the storage that was happening upstream of us, that the flooding through the neighborhood was actually occurring under a 12-hour scenario. So we were able to play all those different scenarios together and find ways to improve the 12-hour condition without hurting the 2-hour condition. So, and we were able, having the 2D grid, it was able to create easy to create exhibits that we could show the before and after flooding to demonstrate to our stakeholders the improvement they would expect to see with the proposed project. So this is an example of the depth grid. And but what I found actually even more useful is, especially when you're analyzing, make sure you understand what's happening to the model, would be to look at one that is based on elevation, so that you could see the various areas where water's ponding. When it's a solid color, that's a level pool, and then as the water color changes gradient, that's where you have water flowing before it moves down to the next pocketed area. Yeah, and then we have a video for that as well, if Teresa wants to kick that off. So, and part of this study was also we were including storage that was north of the school to also mitigate any flow increases that that might happen. I believe that was it for this project.
Yep, and at this point, we can turn things back over to Nicole.
Excellent, thank you. Those were two great case studies, and we're going to go to questions in just a minute or two. I see that some questions have been answered in our questions field, but please feel free to take this time to type in your question for Teresa and Ralph.
Okay, I'll throw this one to Ralph, perhaps.
Sure.
Size of the 2D grid, and can you talk about the 1D, 2D interface entering and leaving the grid?
Yeah, if I remember right, to get it under 10,000, we needed about a 20-foot grid. We were a little concerned that that may be a little too coarse-grained, that it may affect our quality of our results. We did run it again in like a 12-foot grid using a larger license at one point, and the results seemed pretty compatible. So we were pretty gratified in that. You're correct. There are places where you need to add 1D, 2D interfaces. We definitely added one at the upstream side, where the western storage area was overflowing into the 2D grid. We also added some around the various inlets into the storm sewer system.
Okay, we have a question here on if the housing elevations were used to assess ponding. And no, they weren't. An earlier question we talked about while we had the planimetric data on all the buildings, there were even ongoing building removals since 2008, so we had to field check a lot of that, but we didn't account for the actual volume loss in looking at ponding.
That question may have also been, I'm not sure if it was your project, Mike, or whether that was for the Chicago project. For our project, we were using a 2D surface. I don't believe it included the buildings. We did go out and survey some build. Well, actually, we surveyed building elevations to make sure that the ground adjacent was consistent with the what we were getting from the 2D grid, and also to fine-tune the headwater that we were seeking to get to keep the houses dry.
And Ralph, for your project in Illinois there, do you want to talk a little bit about the calibration efforts of the modeling, any past historical information you were able to use?
It was mostly just a discussion with the local village and with their long-term consultant there. If what we were seeing in the model, pattern-wise, was agreeing with what they observed.
Yeah, and here in Cedar Rapids, we had a number of discussions with public works staff, based on past storm events, to know what areas were frequent ponding areas and areas where they needed to have street or road closures. And then in the modeling process too, we had areas that they didn't really necessarily know from a historical basis that were problem areas, but the model showed some issues with pipe conveyance. So it's important in an urban watershed, especially because there's not usually a lot of historical flood accurate data. At least people have recollections of ponding that, but it's important to get to the people that have been through those storm events to verify ponding limits and such.
Yeah, and actually I'm also able to see the questions here, Mike, so let me jump on this one. Talked about the first case study where we had truncated the time window and worrying about whether we're losing hydrograph volume. And one thing you'll see, we're looking to make sure that that isn't a problem or causing a problem. And it may be, if there was a full-on detention basin with a severely restricted outlet. Typically in northeastern Illinois, we're restricting to 0.15 CFS per acre, which is pretty tight. That could be an impact, but mostly what we were looking for is that you would see that when you jump into the middle of the storm, you'll see a little bit of fluctuation as water rushes into the system and kind of equalizes. But that really pretty much equalizes out before it gets to the heavy part of the storm, and it seems to be a pretty smooth curve that seems to work pretty well. I guess, and to add to that, maybe with the nested storm that we're using, the center of the storm is so much more intense than the other parts of the storm that that all of the impact is really measured there pretty directly.
Okay, Ralph. We have one here on the 1D, 2D interfaces. Are we given? Well, I kind of know the answer to this one, but the inlets need to be told the capacity it can receive. So you want to handle that?
Basically, I'm still kind of grappling with what exactly the meanings are and how they work. Basically, we would find times where the water level in the sewer had dropped and there was still water sitting up on the surface, and we that was not the result we expected. So we would add a interface that provides a pretty much an infinite connection between the surface and the 2D grid. I know there are settings in XP Swim that also you can put in inlet capacities. We didn't use that in our models, but if that's a concern, that can also be calibrated. And actually, there's a question after that about the results of the 2D grid, whether you would use that to determine whether the flooding was because of flooding that occurs before it gets to the storm sewer system, surface flow across the surface, or whether that's from undersized pipes. It pretty much depends on how you set that up. In our case, to do the former flooding before it gets to an inlet, you would have to do some sort of a rain on grid. For our projects, all of our hydrographs were input at nodes, and so all of our analysis was flooding from undersized sewers.
Okay, there's question 2 on, we did have pumps in the model for Cedar Rapids because we were looking at various pumping capacities for each of the subbasins to be able to define the pump station cost and capacity for the interior drainage work. We just modeled them as a capacity number, not dynamic in the sense of different pumps on and off occurring. So that way we would get the peak of the pumping capacity was input as steady.
Great, and I think that you guys have pretty much answered all the questions that we had in the oops. Any issues in transfer of flows from 1D to 2D? I think you might have already mentioned something about that, about connecting them.
Yeah, it seems like the normal, just by clicking the box that says connect to 2D surface, that water gets out of the 1D into the 2D just fine. It seems more like there's more of an issue of getting it back off the 2D and into the 1D that you need to add the interfaces.
Great. Well, that looks like it's all of our questions today. Thank you so much to our presenters, Teresa, Ralph, and Mike, and John in the background. Thank you, everybody, for joining us today. Again, if you would ever like more information about HR Grain Services or more information about XP Swim or XP Software Solutions, please don't hesitate to contact us. There's some information there. You are free to email directly at ajain@hrgreen.com to ask about their services, or you can contact one of the XP Solutions offices at the bottom of the screen, or email ameducation@xpsolutions.com. Thank you again for joining us, everybody, and have a wonderful day.